Hello everyone, today I haven't quite gotten around to making another explanation video, and I'm always open to requests and questions and of course any feedback and improvements. But what I have done is I've modified my numerical calculation Excel table because I thought it was still fun to use a software that is absolutely not designed for numerical simulation anyways. I've changed the time steps to 2 seconds, and while I haven't bothered to change the names, so it's still called Moon here, what I have done is I've changed the properties of the Moon to resemble a heavy space capsule on a direct re-entry path from Mars, and I've added atmospheric aerodynamic effects, a very simple aerodynamic simulation, no proper simulation of hypersonic effects, just basic square extrapolation. I've calculated the altitude by subtracting the Earth's radius from the distance between Earth and spacecraft. Then I've made a very simple atmospheric model that is just exponentially declining density with altitude. Then I've calculated the overall speed of the spacecraft by taking Pythagoras and the velocity along each coordinate. I actually haven't properly taken into account Earth's rotation yet, but for a start it's still interesting. Then I take the speed squared times a multiplier depending on coefficient and area and so on. I thought 20 would in that case be kind of realistic, and times the density of the atmosphere at this altitude. I've divided it by the mass to get acceleration. Yet, yes, it's a 100-ton capsule. It's a heavy capsule. It's hypothetical, very heavy capsule. And I fed that back into, wait a second, I've fed that back into the accelerations that I had already created. I divided the acceleration by the ratio between the speed along this coordinate and the overall speed in order to take care of the trigonometry. And then I fed it back into the acceleration. And what I got is essentially a proper re-entry model, not a really detailed or correct one, but for starters, it's fun, it's interesting. And then I've added these values that just put the most interesting parameters in order so I can then print them out on a graph. I'm gonna go through the different columns here real quick. So if you really want to, you could pause the video here and try to replicate it. I'm just gonna put the Excel file in a download link in the description, I think. I followed down an overall of only 372, no wait, the first two lines, 370 time steps. That is, of course, 740 seconds then. And you may notice that the altitude goes below zero. That's because I haven't properly simulated any ground, so the spacecraft just continues on and the atmosphere just keeps getting denser, but this is just a re-entry model, so you can kind of just ignore that and assume that at a sane altitude a parachute would be released and or a slowing down rocket, and the model kind of ends there. Anyway, that gives us some pretty graphs to look at. Now, these two are different windows of the trajectory, and they are slightly warped because, again, Axel doesn't scale the axis equally. But then we have this nice altitude graph. We can see here the spacecraft approaching in at, here the speed graph shows it, velocity, rough velocity. I didn't actually even calculate it, I just had it still in the back of my head, remembering it because I need it quite often. So I had a rough estimate for the velocity coming back directly from Mars. And then it slightly keeps accelerating as it closes in on Earth at an angle. And I even have a sync rate. Wait a second. A sync rate graph, so you can kind of compare that and see the angle. Here it kind of starts hitting the interesting part of the atmosphere that's apparently starts at around 80,000 or something in this model. Actually, the atmosphere in this model continues all the way out into the universe, just exponentially getting thinner and thinner and thinner and thinner. But at a few thousand kilometers, it's actually too thin for Axel to even be in the number range Axel can still deal with. Becomes so small that the kind of floating point variable Axel uses just doesn't work well anymore. Then you can see it keeps descending, it starts slowing down, and it actually has this nice little hole because it's a sort of not well but kind of optimized re-entry path at a kind of well thought through angle, so it kind of flattens out, starts slightly ascending here again. You can see that in the sync rate graph too, that the sync rate becomes negative here for a short time, and keeps and stays for a long time at around 50,000 meters before it then starts descending again. As it falls below orbital velocity, it starts falling down again, and then it just slowly decelerates to terminal velocity and keeps falling. And what I've also done is I've modeled the acceleration, of course, or deceleration, as it is negative, but basically it's the same thing. Here in meters per second squared, so this peak is slightly above 9 Gs, and this one is slightly below 6 Gs. And here, of course, it kind of ends up being at around 0 as it keeps going on at the same speed. The acceleration is actually the change of movement, since I haven't done any relativistic model. Gravity is still an accelerating force, and free fall is not modeled as 0g here. Like this is the actual change in velocity of the ship in relation to the Earth, and not the acceleration that, or the g-force that you would feel inside the ship. So in free fall it's at 0 acceleration. The sync rate and the energy loss, which is simply the acceleration multiplied by the speed, that gives you kind of an idea of how hot the ship would get, though that is actually way more complicated. And you can actually see, though, that this model is a bit inaccurate since the time steps are too big, but for a fun little project I thought this was an acceptable starter. You can see that in the sync rate, I think, very well when we approach terminal velocity and we get to it. It kind of starts oscillating because the time steps are a bit inaccurate, and so as soon as the sync rate becomes too high, the aerodynamic forces become higher. Slow it down, the aerodynamic forces become less, it starts sinking faster, and so it kind of oscillates in its sync rate. You can see a few more. If you like pause and analyze number for number, you can see loads of inaccuracies, but it gives you a nice looking rough idea of a curve of a possible re-entry path. I hope this was sort of interesting. I'll keep continuing this. Of course, this is just a really fun little project. This is far from any kind of accurate simulation, but I'll keep updating it, and thanks for watching.